we are going to prove that the countable union of countable sets is countable. So here first we need to give some notation. So we can call En, okay, these countable sets and the family of these sets, okay, where n goes from 1 onwards, okay, it's a countable family. So just to keep things simple, we can index them with the natural numbers, okay? And let's define S is the union, okay, of all these sets En. Okay, so we want to show that S is countable. Okay. So what we are going to do, we are going to, because all these sets are countable, we can list all their elements, okay? So let's say E1 is a collection of X1, X2, X3, X4, well, and so on, okay? Let me create some more space here. And then I could do this for every set. So I could do it for E2 and so on, right? Let's put a few of them. But you have probably noticed already that there is a problem with the notation here, right? Because the X's, so I'm denoting always the elements with the same letters. So that gets confusing very fast. So let me say for the ones that belong to E1, let me put a 1 here as a superscript. And then for E2, I put a 2. This doesn't mean a square, it's just an indicator, okay? 3. Okay, and 4 for the ones in E4, and so on. Okay, so you see, by doing this, I have created a table, an infinite array, that contains all the elements in all the sets En. Okay. So here, if I want to locate the elements in the set E17, so I need to go to the row 17, and then I will have the elements of E17 listed there. Okay. All right, so now the smart thing here is that we can actually list all the elements in this table. Okay, did you notice the table starts in this corner and then it becomes infinite towards the right and down. Okay, but we can list the elements if we sweep the table diagonally. Okay, then it will continue and so on. So when I do like this, then I get a list that is X11, X12, X21, X13, X22, X31, X14, X23, and so on, okay? The list may not be so easy to write down, but if we look at the table, it's trivial. It's very clear. Okay, what is the construction of the list? You could even decide to separate with semicolons. Okay. Anyway, once we arrange it in a sequence like this, then it's clear that the set is at least, well, at most countable. Okay, so here we have arranged the elements of the union of the en, okay, as a sequence. Okay, so this means we are almost done, because this means that the union is at most countable. Okay. What do I mean by that? You may be wondering, no, wait, it's countable. Well, here comes the problem. So I have created a sequence, but I'm not quite sure if there is repetition. Okay, because these sets E1, E2, E3, and so on, they could have common elements. Okay, I didn't say at any point that they were disjoint. Okay, so some of these elements may be repeated. So I may be counting multiple times each element. Okay, so now we have a list here, a sequence, but there may be repeated elements. So, well, let's call the list L. Okay, so let's weed out the repeated elements from L. Okay, but then you could argue, well, are you sure you didn't take too many elements by doing that? Are you sure you still have a countable numbers, infinitely many number of elements? So the answer is yes. We still keep a countable number of elements because E1 is contained in this countable union. Okay, and because E1 is countable, it's infinite, then the larger set has to be infinite too. Okay, so you see we have proved first that it should be at most countable, and here we are proving that the union must be at least countable. So we are done, it's countable.